Okay, so what we're doing this week is going through all of the previous units, right? We're responsible for units 1 through 7, and the AP exam date is actually going to be on May 14th. I don't know if I told you guys that last week, but I found out toward the end of last week, so it might have been after our last session. So the AP exam date is going to be on May 14th for chemistry, and we're just going back through all these old units. So we just finished unit 6. Now we're going to do 1, 2, 3, 4, 5, and 7. And we did 7 earlier in the year. That's why it's a review for us. So here we've got question number 1, and then there's question number 2, question number 3, question number 4, and question number 5. Okay, and what about question number 6? Number 6, yeah. Let's do the first 6 questions, okay? Let's do the first, or do you want to do the first 3, then the next 3? It's up to you guys. But I would say let's just do the first like 6 questions, and let's give ourselves 6 minutes to do them. And if not all of us are able to get through them all in 6 minutes, that's fine. But I think that should probably be okay for most of us. Does that sound reasonable, gentlemen?
Yes.
Yeah.
Okay, cool. So I'm going to give you 6 minutes to work on the first 6 questions, then we'll go through them all kind of rapid fire, okay?
Yeah.
Perfect. All right, I'm going to pause the recording. Okay, so for number 1, we think the answer is B, because you've got 5 grams divided by 56 grams per mole. That's going to give you an answer in moles, okay? So it's B. Number 2, we've got 21 grams. We want to know how many moles there are. So we need the molar mass, okay, to perform a calculation just like the one we performed in question 1. And then question 3, a 1 mole sample of which of the following has the greatest mass? So you could look at it and do the mass calculations, right? For instance, 14 plus 16 will give you 30. But you can also just look at which molecule has the greatest number of atoms, right? And this guy has as many nitrogen atoms as anything else. And this guy has more oxygen atoms than any other atom, or sorry, any other molecule that's listed here. So that's it, right? D. Any questions, gentlemen?
Nope.
Okay. Number 4. All right. We want to find the atomic mass, right? And that's an average of what you see on the board. So when I look at this, I see, okay, half of it's about 90, and then the other half probably would average out to a little under 93. So if I take the average of 90 and 93, I get a little bit north of 91. And so the closest I would say would be B91. Is that what you guys got, or was my approximation method not good enough?
No,
I wasn't sure about A or B, so.
Well, A wouldn't be high enough, right? Because that's only half the story. So we got to average that thing up a little higher. And I think 93 would be like the average of these guys, not the average, not really including this one. So I think you got to be closer to 91. Let's check. Yeah, that's correct.
Okay, that makes sense.
You could do that mathematically, right? You could do 90 times 52 plus 91 times like 15 plus 92 times 20 plus 94 times 20 plus 96 times like 4, all divided by 53 plus 15 plus 20 plus 20 plus 4, right, as a quantity. And if you did that, you'd get roughly 91, or you'd be closer to 91 than you would be to 93 or 94. Okay?
Okay.
All right. And we've gone through this a bunch of times, so. Okay, this one here. All right, so this is, I'm curious because I don't have my periodic table open, so I don't know which one this is. But it's something close to one, the average mass here is close to 157, right? So what's got an atomic mass that's close to 157?
is GDB.
Yeah. Gadolinium.
Yeah, gadolinium, Okay, so GDB, gadolinium it is. Nice job, gentlemen. Any questions about this one?
Nope.
Okay. All right, so the average mass here, right? You've got a little bit more 187 than you do 185. So is it going to be greater than or less than 186?
Greater than.
Greater than, and just a little bit, right? So that puts you at 186.3. Any questions?
No.
Okay.
Nope.
There we go. All right, so how did we do on that? Did we need the full 6 minutes, or was that more like we got through it in 3 minutes?
I felt like I got through that really quick.
Yeah, pretty easy.
Okay, let's go through the next ones a little bit faster then. Question 7, blah, blah, blah. Okay, 7, 8, All right, 9. 10. 11. 12. 12. Okay, let's do this. Let's go ahead. We got 6 questions to do. They're a little bit longer. There's a little more reading involved. So let's go ahead and take, I'll set the timer for 4 minutes and we'll see how that goes. Okay, that might be a good match there. All right.
Sounds good.
All right, gentlemen. Okay, so a student obtains, let me just double check really quickly. I want to make sure I haven't gotten any emails from like anybody else trying to get in or something having Zoom issues, but I think it's doubtful in my. Okay. No, okay. Doesn't look like it. Okay. All right, guys. So a student obtains a 10-gram sample of a white powder labeled barium chloride. After completely dissolving the powder in 50 milliliters of distilled water, the student adds excess sodium sulfate solid, which causes a precipitate of barium sulfate to form, as represented by the equation above. The student filters the barium sulfate, rinses it, and dries it until its mass is constant. Which of the following scientific questions could best be answered based on the results of the experiment? Okay. Okay, so okay. So result of the experiment. All right. Okay. Yeah. So, okay. What did you guys get for this one? I had to think through this a little bit, but as soon as I visualized what was happening, I was confident in my answer. But what do we think?
I wasn't sure, but I chose C, and I was thinking maybe also B.
Okay. So Jacob's between C and B. What do you think, Antonio?
B.
Okay. Peyton?
And B as well.
Yeah. So with this one, okay, you've dissolved 10 grams of barium chloride, right, in water completely. So you don't know what the molar solubility is because you haven't dissolved to the point of saturation. You see what I'm saying?
Mm-hmm.
Yeah.
So like, if you just keep adding barium chloride until you can't add anymore, until it won't dissolve anymore, then you can calculate the molar solubility. But at this point, we haven't overwhelmed the solution capacity of the water, so no. Okay, like the water can still dissolve the barium chloride, so we don't know what the molar solubility is, but B ends up being correct, and I had to really think through and visualize this thing. So here's what happens. So you dissolve this barium sulfate in water completely, right? So all the barium is in solution, okay? And so then what you do is you add sodium sulfate to pull out all of the barium from a solution. So you completely remove all the barium from solution. And then you have some mass of barium sulfate, right? It's a you know, it's powder or whatever, you dry it and you've got some mass, right? So because you know the formula for this ionic compound, and because you know all of the molar masses of its constituent atoms, you can go ahead and calculate exactly how many moles of barium you have in your final product. Okay, you can calculate the number of moles here. So then you can ask yourself, okay, if I've got this many moles here, would I expect to have had that many moles from 10 grams of barium chloride? If the barium chloride were pure in the first place. If I've got fewer moles than expected, right, then I can say, okay, I've got 97% of the moles of barium I expected to have. Well, then my barium chloride was 97% pure. Okay.
Mm-hmm.
Yeah. And it's actually an easier calculation than I kind of went through, because if you've got the number of moles of this, you can say, okay, we should have a 1-to-1 molar ratio of this to this. So how many moles of this should I have in 10 grams versus how many moles of this should I have when I've done my purification, right? And that's the only ratio we need actually. Okay.
Sounds good.
Okay. All right. Number 8. A student measures the mass of a sample of a metallic element M. Then the student heats the sample in air where it completely reacts to form MO. The student measures the mass of the compound that was formed. Which of the following questions can be answered from the results of the experiment? Okay. So what do we think here, gentlemen?
I'm thinking B.
Which now? Which one?
B.
B.
Yeah. Got B
Okay.
as well.
Molar mass of M. Okay. Yeah, that's right. Okay, you can totally do that because you know that it's MO, and so you know exactly, you know how much M you started with, and then when you form this compound MO, if you've got the mass of the compound right, you can say to yourself, okay, well I know it's MO, and I've got this mass, right? So all the additional mass is from oxygen. So then I can say to myself, okay, so this many moles of oxygen were added, and now I can use that to calculate the molar mass of M because there's a 1-to-1 molar ratio. So I've got exactly as many oxygen atom moles or moles of oxygen as I do of M, right? And so I can divide the mass of M that I already have by the number of moles of M, which equals the number of moles of O, right? And get the molar mass of M. Okay, all good on that?
Yeah.
Yep.
Okay, number 9. So a 42-gram sample of a compound containing only carbon and hydrogen was analyzed. The results showed that the sample contained 36 grams of carbon and 6 grams of hydrogen. Which of the following questions about the compound can be answered using the results of the analysis? Okay, so what do we get for this one, guys?
I'm thinking B, but I also think D as well.
Okay,
I'm
what do you
thinking
think?
D.
Antonio says D, and Caton?
D.
Yeah, this one's D. So the reason, Jacob, that it's not B, and that's the distinction we need to make here, is that you don't have any information at all on molar mass, right? All you have is this ratio of masses. You don't know how many grams per mole this molecule is, and you don't have any information on the molecular formula. Okay?
Okay.
Yep. All right. So now we've got, what is this? We've got, okay, this table with masses. So a jar of sodium chloride contains a powder. And the table above contains information determined by analyzing a sample of the powder. Which information in the table is most helpful in determining whether the powder is pure sodium chloride? So what we get, gentlemen?
B.
B.
Yeah, I got
Okay.
B as well.
B. Yeah.
B. Yeah. Okay. I don't think any explanation is needed, but basically what you have here is that if you've got 35.2 mass percent sodium, you can say to yourself, okay, is this the same mass percent sodium as we would expect for pure sodium chloride? If it's not, then we don't have a pure sodium chloride sample. So that's absolutely correct. Good job. And then number 11, a student obtains a mixture of chlorides of 2 unknown metals, X and Z. The percent by mass of X and the percent by mass of Z in the mixture is known. Which of the following additional information is most helpful in calculating the mole percent of XCl and of ZCl in the mixture? All right, what do we think?
The molar mass.
Yeah, B.
B.
We have to
B.
have those, right? Because if we don't have the
Yeah.
molar masses of X and Z, we can't calculate the mole fractions of X and Z and then go from there. Okay? So that's the issue. All right, so B is very important. Okay. And then a vessel contains a mixture of gases. The mass of each gas used to make the mixture is known. Which of the following information is needed to determine the mole fraction of each gas in the mixture?
Would it be A?
Yeah, for sure. Is that what you got, Jacob and Caton?
Yeah.
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 I agree. A.
Yeah. Yeah. Because if you want mole fraction, you got to have molar masses and masses, right? And so, so A is necessary. Very good. Very similar to the last problem. Okay. So mole fraction, for those of us who might not remember, is just number of moles of X divided by the total number of moles of all elements in the compound. Okay. or in the sample. In this case, it's a sample of gases. All right, so so let's take a look. So we got electron configuration for 13, and then another electron configuration 14, another electron configuration 15, and then 16 has this binding energy thing. 17 has a binding energy, 18 has a binding energy, 19 something different. Okay, so I think we should do 13 through 18, and I feel like we can probably knock this out in about 4 minutes. So let's just do a check-in at the 4-minute mark, okay?
Okay.
All right, guys. So hey Siri, set timer for 4 minutes.
Okay, your timer is set for 4 minutes.
Okay, so number 13 here. How many unpaired electrons are in the atom represented by the electron configuration above? Okay, what do we think, guys?
0.
A.
Yeah, no unpaired electrons, right? That's just a full valence shell there. Okay, end of story. And then oxygen atom in the ground state. What do we think?
C.
C, yeah, it's C, and it's not D, right? And that's the important distinction to make. Electrons would rather be separated like this. They'd rather occupy their own orbitals, if at all possible, than be paired. Okay, so this is a higher energy configuration. This is an excited configuration, whereas this is a ground state configuration here. Okay?
Okay.
All right. Which of the following is the correct electron configuration for a ground state atom of magnesium, atomic number 12?
C.
Yeah, go C.
Yeah, for sure. Good job. And then the complete photoelectron spectrum of an element is given above. Which labeled peak corresponds to the 1s electrons and y?
B.
B as in boy?
Yes.
Yeah.
Yeah, that's what I got as well.
Yeah, Antonio, did you get that too?
Yeah.
Yeah. Yep, there are more of them. So do we know what atom this is? Can we say which atom it is?
Lithium?
Yeah, right?
Yeah.
You've got 2 1s electrons, and then you've got 1 2s electrons. That's lithium. Yep. Okay. And then here we go. Borons represented above. Why is this consistent with the electron shell model of the atom?
B, right?
Yeah, I felt like B was the only one that was even correct. Except no,
Yeah.
A is correct too. A is correct too. Yeah, but I think equal numbers of electrons in the first and second electron shells. I mean, I don't know, because I don't know how you conceptualize the shell. Like,
Yeah.
do you think of like the shell is normally when we draw those shells, we draw the second shell including 2s and 2p. So I kind of don't like this.
Right.
And then 3 electrons with the same binding energy in the second shell. No, they don't have the same binding energy. So B is the only decent answer. So
Okay.
I'm gonna go with B. Let's just double check that that's correct. Yeah. Okay. And then number 18, the complete photoelectron spectrum of the element carbon is represented above. Which of the following best explains how the spectrum is consistent with the electron shell model of the atom? Okay, what do we get here, guys?
B is the only one that kind of makes
Yeah.
sense.
B.
Yeah, I agree with that. Yep, that was the only one that I liked too. So there we are. Good job. Very good job. Okay, so now we've got 6 more. So we've got atomic radii question, and then another atomic radius question, and then ionization energy, which is related to atomic radius, ionization energy again, and then, okay, and then we've got reaction question, and then aluminum question. Okay, I think these are all good to do together. So let's take 4 more minutes to do these. Hey Siri, set timer for 4 minutes.
Okay. Your timer is set for 4 minutes.
That's hilarious. Resume. Okay. All right, so number 19, the atomic radii of the elements in the nitrogen group in the periodic table are given in the table above. Which of the following best helps explain the trend of increasing atomic radius from nitrogen to bismuth? All right, what do we get here?
C.
Got C.
The attractive force between the valence electrons, increasing atomic radius. The attractive force between the valence electrons and the nuclei of the atom decreases. That's true.
Yeah, and then just none of the rest of them make sense.
Yeah. Yep. Okay. C. Yep. All right, we're moving on. That was what I got too. Looks strange to me on second read though. But yeah, that's right. Yeah, that's totally true. Yeah, that makes perfect sense. Okay, there we go. All right. So there's less attractive force, so they can be farther out. That makes sense. Okay, so which of the following helps to explain why the atomic radius of potassium is greater than that of bromine?
Okay.
So what do we think?
D.
I got B.
Yeah, D is in dog. That's totally true, right? So the effective nuclear charge experienced by the valence electrons is smaller for potassium than it is for bromine. Are potassium? I don't have a periodic table open. Are potassium and bromine in the same row?
Yes.
Yes.
Okay. So then what's happening is that as you go across the row, you're not gaining an extra valence shell. So the effective nuclear charge is increasing across the row. And that's a calculation that'll be worth looking at later on. Which of the following best helps explain why the first ionization energy of potassium is less than that of calcium? So this is just the same thing. This is just C, right? So the valence electron of potassium experiences a lower effective nuclear charge than the valence electrons of calcium. Yeah? We all get C for this one? Okay. Yeah, same thing. Okay, 22. Which of the following best helps explain why an atom of rubidium gas has more easily loses an electron in a chemical reaction than an atom of lithium gas? Okay, what do we think, guys?
D.
Yeah, D.
B as well.
In the rubidium atom, the valence electron is farther from its nucleus than the valence electron of a lithium atom is from its nucleus, and that's true, right? So as we go down a group, okay, the outer shell electrons get farther and farther away from the nucleus, and they are therefore more easily abstracted in chemical reactions. Okay. So Rb reacts with oxygen in a mole ratio of 2 to 1. Which other element below will do the same?
I got
B.
B, cesium.
If you're in the same group, you react in the same ratio to form ionic compounds, generally speaking. Okay, so 24. What charge does aluminum typically have in ionic compounds, and why?
C, right?
Yeah, +3 because it has to be valence electrons. Very, very good. Okay, any questions about those, gentlemen?
No.
All right, so I'm going to close out of this, and then we'll go to the free response questions. So let me unlock the FRQ. Assessment now, let you see your results. AP Chem. Why can't I give this to you? Okay. Why won't this just assign? What the heck? Guys, did we finish all of the Unit 6 stuff? Yeah, we did.
I'm pretty sure.
Unit 6.
Yeah,
We went to
yeah.
FRQ as well.
Okay, I don't know why this thing's being a pain. All right, well, this is what I'm going to do. I'm going to go back. I don't know why this thing is being a pain, but I'm going to go back, and then this thing just doesn't want to unlock for reasons that make no sense to me. Okay, it looks like it's already assigned for you or whatever. I don't know. But, all right, cancel this. Let's just look at the questions. Can you guys get to these questions?
Check. No, we cannot.
Yeah, not yet. I'm doing the refresh dance over here.
Okay, there's some kind of jive situation. I don't know why that's not assigning to you. Like I can't, normally I can like click. It's like, I don't know why it says it's already assigned or something. I don't get it. So I don't know why it's being weird. Maybe I assigned it early. I don't know. Whatever the case, we'll just do this on the computer then. Can you read my computer screen well enough?
Yes.
Yeah.
Okay. So question 1 has how many parts? It's got 4 parts. Let's do the first 3 right now since we can read them, okay? So for parts of the free response question that require calculations, clearly show the method used and the steps involved in arriving at your answers. You must show your work to receive credit for your answer. Examples and equations may be included in your answers where appropriate. Okay. So I'll mention this when we're back in the whole group, but I'll tell you right now, what you're going to have is a 45-minute test that's all free response. It's going to be open note, open computer, open Google, right? So you can Google whatever you want. You can do whatever, you can find whatever information is at your fingertips. You shouldn't have anybody, you shouldn't have anybody else in the room with you, right? So you shouldn't be cooperating or like chatting with other people, etc. The College Board is going to be really strict, and it's also going to be really good at detecting cheating. So don't cheat, right? Like just be as good as you are at this and call it a day. So use your understanding, and it's going to be, I think it's going to be highly conceptual. So they're going to give you a lot of questions that are going to be really difficult to like Google and whatnot. So, you know, you're going to have to know what you're doing. You can write your answers down on paper and take a photo and upload them. You can also type them out in the test window or whatever. That's about as much as I know about how the test is going to work, but I would just say be on your game, right? So it's going to all be free response. There won't be any multiple choice, which is fine. But at the same time, that means that you're just really going to want to be, you know, on your game in terms of like getting it all done. And I just don't know how many questions they're going to ask in 45 minutes. Like this is a bit of an unknown. So you could see, I mean, you could see stuff from all over the place. You could probably see, I mean, I feel like you should expect to see material from all 7 units, but I just don't know what the weighting is going to be, or if it is going to be the weighting that's you know, that we were told to expect at the beginning of the year. So we'll see. This is a new situation, but the really good news is we can still take the test and we can still earn our college credit. And we've all done a really good job preparing, and we are still doing a good job of preparing. So I think that by the time the test date gets here on May 14th, which is, you know, a little over a month from now, I think we're going to all be just ready to rock and roll. Okay.
What about calculators? You know,
Yeah, for sure. Calculators are fine.
Okay.
Yeah, you're allowed to have them. And I'll try to figure out a way to get you your calculators. I've got them, so I'll figure out a way that we can get them to you, okay?
Cool.
We can probably mail them. I just don't, I'll check with Dr. Ward. I'll have a meeting with her next week. Okay?
Sounds good.
All right, guys. And then let me just write that down in my notes real quick. So there we go. Okay, so I'll talk to Dr. Ward about that. And if I forget, then I'll email her. We'll get this done. Okay. All right, so is this thing recording? Good. Okay, so answer the following questions related to potassium. In terms of atomic structure, explain why the atomic radius of potassium is larger than that of sodium. Okay, and then in terms of atomic structure, explain why the first ionization energy of potassium is less than that of calcium. And then potassium forms the compound K2O, which is an ionic compound that is brittle. Identify another element M that is likely to form a brittle ionic compound with the formula M2O. Justify your answers in terms of periodic trends. Okay, this shouldn't take us too long. Let's just take 3 minutes to look through these and then we'll talk through them, okay? So, hey Siri, set timer for 3 minutes.
Okay. 3 minutes
Your
and
timer
counting.
is set for 3 minutes.
Thank you, Siri.
Yeah.
Okay. So for parts of the free, okay, so number one, right, in terms of atomic structure, explain why the atomic radius of potassium is larger than that of sodium. Okay, so what's going on there, guys?
I was thinking it's greater because it has an extra shell, therefore giving it a greater radius.
Exactly, right? So I'm trying to pull up the periodic table here. God, why is it so? Google for p-table and it doesn't give you ptable.com, which is weird. So I want that. Okay, so if you pull this guy up, you see the potassium is one row below sodium, and so potassium, yeah, exactly. It has an entire extra shell, so that's exactly correct. Sodium's electron configuration is 1s2, 2s2, 2p6, 3s1, whereas potassium's is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So it's got a whole extra shell. That's correct. Good. Any questions, gentlemen, about part A?
Okay. So just as long like the part that tripped me up here was the terminology. So it's because it has an extra shell, right?
Yeah, it does.
Okay.
Yep. I mean, it's potassium's outer shell is the 4s shell, whereas sodium's outer shell is the 3s shell.
3s shell, right?
So, yeah.
And so that gives it the greater what is it, electron shielding?
Between yeah, exactly. Yeah. So potassium's got an extra inner shell. So sodium's inner shells are 1s, our principal energy shells 1 and 2, whereas potassium's inner shells are principal energy shells 1, 2, and 3.
Okay.
Yep. Okay. So in terms of atomic structure, explain why the first ionization energy K is less than that of calcium.
Okay.
The first it should say the first ionization energy for potassium is less than that of calcium. Okay. So what do we think?
So each of the valence electrons of calcium has a greater effective nuclear charge.
Yeah.
And in order for it to get to a stable configuration, it needs to lose 2 electrons instead of just 1, which is the case for potassium.
Yeah, exactly. So the effective nuclear charge for calcium is greater than the effective nuclear charge for calcium. For potassium, sorry, the valence electrons experience. That's true. Yep, perfect. And then, okay, so part C. Potassium forms the compound potassium oxide, which is an ionic compound that is brittle. So find another element M. So what would you say is another element that could form a brittle ionic compound with oxygen?
Would it be anything in
anything in group 1 except for
hydrogen?
Yeah, hydrogen forms water, right? That's not a brittle ionic compound, but everything else, yeah, lithium, sodium, rubidium, cesium, francium, those would all do.
Okay.
Because they're in the same group, right? So elements in the same group tend to behave similarly and form compounds with similar properties. So we should expect that sodium oxide and lithium oxide and rubidium oxide and cesium oxide and francium oxide would also be brittle ionic compounds. Okay, that's true. All right.
Is there any time that those wouldn't be brittle?
Shouldn't be. Those should always just be brittle ionic compounds. Okay. Yeah, I don't know. I mean, the only things you could do to them to change their physical properties would be to change the physical environment. So you could heat them or cool them or change the pressure to which they're exposed. But I don't see that having an effect on their brittleness.
Thanks for sitting in my backpack.
All right.
Okay.
Althea says hello, by the way.
Who says hi?
My dog.
Oh, nice. Okay. So the compound, K2O2 also exists. Okay. A chemist can determine the mass of K in a sample of known mass that consists of either pure K2O or pure K2O2. From this information, can the chemist answer the question of which compound is in the sample? Indicate yes or no and explain. So what is this? Chemist can determine the mass of potassium. Oh yeah. Okay. So can the chemist answer the question and indicate yes or no and explain? Okay. So take like a minute or so to go through this one, and then we'll resume. Okay. So take about a minute here. What do we think?
Yes, he could.
Yeah, they can, right? And why? How would you explain that, Antonio?
Well, if you could know the mass of K, you could also know the mass of O, right?
Yeah.
And from that, you could see if it's K2O, K2O2.
Yeah, provided that you've got the mass of the whole sample. If you can get the mass percent, then you're good to go. Yeah, because it's a sample of known mass. Yep, exactly. So you can just use your mass percent. Yep, exactly. Okay, let's move on to question 2. All right, so for parts of the free response question, blah, 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 that's the rule. A sample of a pure element is analyzed using a mass spectrometer. The results are shown below. Okay, so you've got this percent abundance, and you've got this atomic mass. Okay. So how many different isotopes of the element were in the sample? And then describe how to use this information from the mass spectrum to determine the average atomic mass. And then identify the element and write a ground state electron configuration of the atom of the element that you identified in part C. Okay, so this is pretty straightforward. So here's this one. So how many different isotopes? Let's just talk through this one, guys. I don't feel like we have to spend a bunch of time going through like each one individually. So, okay, how many different isotopes do we see here, gentlemen?
3.
1, 2, 3. Yeah, that's it. Okay, good. And then describe how to use the information from the mass spectrum to determine the average atomic mass. Okay, so what would you do?
Okay.
How would you get the average mass?
Well, it's mostly going for 24, but it's going to be a bit smaller, right? Since you also have 25 and 26.
Yeah, so what I would do in this case is I would do 24 times like 0.79 plus 25 times 0.10 plus 26 times 0.11, right? And I would write that calculation out and I would just put it down, okay? And that's what I would do mathematically, right? And then I would write a little English sentence and I would say, the calculation shown provides a weighted average from the information in the graph, period, right? And I would be done with it. Like I would say that's all I would say, okay? So does that make sense or do we have a question about that?
That makes sense.
Good.
Okay. Yeah, that's how you answer one of those questions successfully. Like they just can't mark you off for that. Like you would have done the right job. But we can also look at what the answers look like too. We can like look at those. I don't know where the heck are they? Right there. Okay. Identify the element. Okay, so this thing has an average atomic mass of 24 point something. So it's magnesium. Thank you, Antonio. And then the ground state electron configuration. You can do that with your hands tied behind your back. Okay. So let's just look at the answers and like how they score these things and what they say, like how do you get your points, right? So that's what I'm interested in. So part A, you just have to talk about the 3 isotopes. That's it. This is just easy. Part B, yeah, so you would actually show the weighted average. That's exactly what I said. Yep. Okay. And then part C, you just say that it's magnesium. Part D, you just do that right. Okay, that's it. That's exactly what we had. Let's look at the responses for part 1 and just see what they would want you to say. So part A, okay, indicates one of the following to get a point. Okay, we talked about that. Part B, because an electron is removed, is less strongly attracted, fewer protons than calcium. So you've got to say something about fewer protons or a smaller effective nuclear charge. I think that would be okay. The response meets both of the criteria below. Okay, so one of them, and then you talk about that it's in the same family. That's exactly what we said. The chemist can determine the identity of the compound. Yes, yes, yes. Mass percentage. Yes. That's exactly right. Exactly what we said. Okay, so we did a really good job. We really knocked that out. Okay, so I'm gonna pause the recording.